Hi folks, this is going to be our final lesson on solving systems of equations, in particular 3 equations and 3 unknowns. So I just want to review what we did in the last video. So what we did is we took a system of equations, and instead of using our traditional method of using elimination, what we did is we created a matrix which used only the coefficients of the variables and the constant. Okay. Reason being that those are really the only things we're manipulating when we're using whether it's substitution or elimination. The x, y, and z never change. So we just don't write them all together. Okay, so what we did is we started off with our matrix and we used our elementary operations. In this case here, instead of applying to equations, they're applying to rows. And we were able to reduce this matrix to this form here. Okay, what's important about this form is that our last line has 0 coefficient of x and y and a coefficient of 1 for z. So I can read off from this last line the value of z. In this case here, z equals 3. And then I could work backwards, okay, to the previous equations to use row 2 to determine the y value, and then take those 2 answers and use row 1 to determine the x value. Okay? So it was about getting it into this row echelon form. Okay? This process is what's called Gaussian elimination. I guess a little later on, someone had the idea of not stopping at this point here, but actually going on with our reduction of the matrix, and instead to keep going till we have this scenario. We again still have our leading one, and then our diagonal. So here, coefficient of y 1 and coefficient of z 1, and still have our triangle of zeros. But instead of keeping numbers here, we keep reducing to get a 0 in this position and zeros in these positions, and then have just our 3 constants representing the right-hand side of the equation. So if we keep reducing the matrix to this form, we can just read off the answers straight from the matrix. So here, z would be just equal to whatever number that is, y would be equal to whatever number that is, and x would just be equal to that number there. Okay, and this is what's referred to as Gauss-Jordan elimination. So that's what I'm going to do now, is I'm not going to redo this whole problem or do another problem. I'm just going to continue from this point here. Okay, so as you see, I've just written the last step. Okay, and our goal is to put it in what's called reduced row echelon form. Sorry about that. Okay, so let's go ahead and do that. Okay. Now the reason why this is fairly easy to do is because we have these zeros, okay, in row 3. So remember how we used row 1 to eliminate these 2 coefficients. We're not going to go backwards. We're going to use row 3 to eliminate those coefficients. And the reason that works is because these are already 0, so they won't affect either of the x and y components in the first 2 rows. Okay, so let's do that here. So the first thing I'm going to do is I'll get rid of this negative 13. So I'm going to multiply row 3 by 13 and then add it to row 2. Okay, so 13 times row 3. I'm going to add that to row 2, and then I'm going to replace row 2 with that. Okay, so let's see what happens. So here, 0, 0, 1, 3. Okay, that's not going to change. Okay, so let's see what happens. Again, 13 times 0 plus 0 doesn't change this first term of 0 as we want. Okay, here, 13 times 0 again, 0 plus 1. Still equal to 1. Okay, we want that one there. It hasn't changed. But now we've got 13 minus 13, 0. Okay, exactly what we wanted. 13 times 3 is 39 minus 37, and that's equal to 2. And we see that we can read off the answer for y equals 2, which is exactly what we found earlier on. Okay. Now, because I didn't do anything with row 1, I can actually perform that operation in the same step. Okay, so here, let's see what we're going to have to do. I'm going to multiply row 3 by negative 4. and then I'm going to add row 1 and replace row 1. Okay, so again, this is just 0, doesn't affect that first term in row 1. This is again 0, even though I'm multiplying -4, doesn't affect the second term in row 2. But now -4 plus 4 is equal to 0. And then here we have -12 plus 11 is -1. Okay, so our last step here is just to eliminate the second term in row 1. And we see now that I can use row 2 to do that, because I've got zeros on either side, so nothing else will be affected. The only thing that will be affected is the y coefficient. Of course, and our constants here, but we don't worry about that. Okay, so what I'm going to do here is I'm going to have to, well, in fact, I just have to add row 1 and row 2, and that'll cancel out the second coefficient. So here, row 1 plus row 2, and I'm going to replace row 1 with that resultant. Okay, so the bottom here doesn't change, 0, 0, 1, 3. This doesn't change, 0, 1, 0, 2. And now let me do R1 plus R2, so 0 plus 1, that doesn't change. 1 minus 1 is 0, exactly what I wanted. Here, 0 and 0 doesn't change. And here I've got 2 minus 1 is equal to 1. Okay, and what we have here is reduced row echelon form. And from here we can just read off the answers. Okay, we see that x is equal to 1, y is equal to 2, z is equal to 3, exactly the answer we got before. Okay, so again, at this point here, when we're working with 3 equations and 3 unknowns, it's personal preference. That if you're using a matrix, whether you want to stop at Gaussian elimination and then have to do the substitution back into the previous equations, or if you want to just keep going, you see it's quite simple, especially when you're working with integers, and you can continue on with the Gauss-Jordan elimination. So you should just be able to read the answers straight off the matrix itself. Okay, so as with solving any system, the way to get used to using these matrices is just to practice. Okay, and as before, you need to be very careful with your arithmetic, especially when it comes to the signs, because one little sign error will create lots of problems, as you can imagine. Okay, so start practicing these, please.